All furnaces require a supply of air for proper operation. A furnace's air system ensures that the correct amount of air is delivered to where it's needed for proper combustion. The gases produced during combustion transfer heat to the furnace tubes and then flow up the stack. The flow of air and combustion gases through a furnace is generally known as draft. Furnaces are often identified by the type of draft that they provide. For example, two common types of furnaces are forced draft and natural draft. A natural draft furnace works much like a fireplace and a chimney. Heat from the fire in a fireplace warms the air in it. The heated air in the fireplace is lighter than the cooler air outside, so it rises through the chimney. This reduces the pressure inside the fireplace. As the hot air rises, it's replaced by cooler, heavier air in the fireplace, and the process continues. In a natural draft furnace, the hot combustion gases, which are lighter than the outside air, rise up the stack and create a lower pressure in the furnace. As this occurs, cooler, heavier air from outside the furnace is drawn into the burners through the air registers. Airflow through a furnace is produced by a difference in pressure. In an operating natural draft furnace, the pressure inside the furnace is less than the atmospheric pressure outside. As a general rule, as the difference in pressures increases, the amount of draft in the furnace also increases. The pressures in various areas of a furnace are typically measured by instruments called draft gauges. Draft gauges commonly indicate pressure measurements in units of inches of water. These gauges are used to determine the flow of air and combustion gases through the furnace. In a natural draft furnace, the height of the stack affects the amount of draft that can be produced. In general, if all other airflow conditions are equal, the taller the stack, the greater the draft. This is because a taller stack creates a greater difference in pressure. Often, the amount of draft must be adjusted for proper operation of the furnace. Since the height of the stack cannot be adjusted, another technique is used. In some furnaces, the draft is controlled by the position of a damper inside the stack. Changing the position of the damper makes the outlet for the combustion gases larger or smaller. As the outlet gets smaller, draft decreases. As the outlet gets larger, draft increases. Air and combustion gases are moved through forced draft furnaces by fans. This is a simplified illustration of a forced draft furnace. A fan, called a forced draft fan, draws air from the atmosphere and forces it into the furnace. On this furnace, the burners are mounted along one wall. The combustion gases flow through the furnace and then out through the stack. In a forced draft furnace, airflow is controlled by coordinating the positions and operation of the stack damper, the burner registers, and the fan. Some forced draft fans have dampers or louvers on the discharge side of the fan. These dampers can be opened or closed to allow more or less air to flow into the furnace. On other types of forced draft fans, the dampers are located on the inlet side. Adjusting the inlet dampers increases or decreases the amount of air that is admitted to the fan and into the furnace. Another type of furnace is a balanced draft furnace. A balanced draft furnace is similar to a forced draft furnace, but it has another fan in addition to the forced draft fan. The second fan is called an induced draft fan. It is located in the flow path of the combustion gases between the furnace and the stack. So, in a balanced draft furnace, one fan provides air for the burners, and the other fan removes the combustion gases. Furnaces are used to heat many different types of process fluids. As the process fluid circulates through the tubes inside the furnace, it receives heat that is produced by burning fuel. This particular furnace is floor-fired. The process fluid enters the furnace through these tubes in the convection section. This arrangement allows the fluid to be preheated by the combustion gases before it reaches the radiant section of the furnace. Preheating the process fluid makes it possible to bring it up to the desired temperature while burning less fuel. In other words, it makes the furnace more efficient. From the convection section, the process fluid passes through the tubes in the radiant section. The process fluid becomes hottest in the radiant section because more heat and higher temperatures are available. Regardless of the design of the furnace, the tube arrangement has to allow for a continuous flow of process fluid. For example, these tube ends are connected with tubing bends. In other tube arrangements, the tubes are connected together by enlarged sections of pipes called headers instead of tubing bends. The route that the process fluid takes as it flows through a furnace depends on the design of the furnace. Each continuous, uninterrupted path that the fluid takes is called a pass. This furnace is a single-pass furnace, but many furnaces are multi-pass. The flow rate of process fluid through a furnace is regulated by valves. There's usually a control valve for each pass. These valves are often operated automatically as part of a control system. The proper flow of process fluid is critical to proper furnace operation. Flow problems can lead to heat transfer problems as well as equipment damage. One type of problem that can occur is called coaking. Coaking is the accumulation of carbon deposits on the inside walls of the tubes. Crude oil and some other types of process fluids tend to leave carbon deposits behind as they're heated and flow through the tubes. Coaking makes the inside diameter of a tube smaller, and it can restrict the flow of process fluid. It can also lead to heat transfer problems. Carbon deposits insulate tube walls, which reduces the amount of heat that is carried away from the tube by the process fluid. If this situation is not corrected, the tube could overheat, weaken, and eventually rupture. Coaking can also develop if the burner flames come into contact with the tubes. This problem is called impingement. Impingement can create hot spots on the tubes that can lead to the formation of carbon deposits. If the impingement problem is not corrected, the tubes could eventually rupture. In multi-pass furnaces, the flow of fluid through the tubes can present additional problems. In addition to flowing at the proper rate, the process fluid should move evenly through all of the tubes in the furnace. If the flow is not even in all the tubes, the fluid will not be heated evenly. As a result, the temperature of the fluid leaving the furnace may not be within the specified range. Also, if the process fluid moves too slowly in a furnace, the likelihood of coaking and its associated problems could increase. In this topic, we looked at how air flows through natural draft furnaces, forced draft furnaces, and balanced draft furnaces. We also looked at how process fluid circulates through a furnace and at conditions that affect flow through the tubes in a furnace.